Let's find the average rate of change. Your paper will be corrected, I just corrected mine, of g on the interval from pi over 2 to pi. Okay, we don't even need a calculator for this, but looking at the vocabulary, average rate of change is the slope between 2 points. I just really want to know the change of y over the change in x. I'm looking for slope. Rise over run, change of y, change in x, basically the rate of change. And so let's start. I want to know what happens if I plug in a pi, and what happens if I plug in a pi over 2. And I'm going to subtract those. And in the denominator, I'm going to do pi minus pi over 2. Okay, let's do the easy part first. Pi minus pi over 2 is, well, half a pi. If I plugged in a pi into the g function, and I'm going to sidetrack for a second here. We'll do a little bit of work over here on the side. G of pi would be sine of pi minus 2 cosine pi. And let's see, sine of pi is 0. Cosine of pi is -1, so we have positive 2. There we go. We could do that in our head. I chose not to. Didn't want to do too much in my head on a video. You lose the visual of it. So then we have sine of pi over 2 minus 2 cosine pi over 2. All right. Sine of pi over 2 is 1. That becomes 0. And therefore, we will have, well, 1. All right, so the numerator is 1. The denominator is pi over 2. That means I have 1 divided by pi over 2. I'm going to show a step that I hardly ever show, but this is 1 divided by pi over 2. Don't do this every time. This is just a shortcut that happens in my head, but why it happens is what I'm showing you. We multiply by the reciprocal, and we have 2 over pi. So the average rate of change is 2 over pi. Okay, let's use the table of values to find each of these. There are 2 little questions that go along with this. I want to find the average rate of change, so slope, for h of x on the interval from 1 to 6. Don't make it harder than it is. The change in y over the change in x. Well, the denominator is 5. What's h of 6? I don't know. Good thing I have a table. 6 up, 14. There we go. 14 minus 1. -6. That gives me 20 over 5, so it's 4. I don't know what it represents, but the slope from 1 to 6 is 4. We just basically use slope. This is y2 minus y1 over x2 minus x1. That's exactly what we just did, okay? We did the same thing here, only we had to plug it in to figure out what the y's were. Find a reasonable approximation for the instantaneous rate of change. Okay, whoa, what? Instantaneous rate of change, what's that? Well, that's the slope at one specific point, and they're asking for an approximation. So we're not ever in this context going to be able to tell you exactly what it is. So I need just a reasonable approximation for the instantaneous rate of change at x equals 5, okay? There's more than one way to do this. I want to know basically what the slope is around here. I'm going to give you more than one answer. And in a free response question, they would probably include all of these answers as reasonable answers. So the slope at 5, first of all, the slope at 5 is not 6, okay? The value of the function is 6. That's not the slope. But the slope at 5, don't know it, but I could find some points around 5 and estimate the slope around 5. So I'm going to do this one 3 different times. I'm going to find the slope on the interval from 4 to 5, and that could estimate what happens at 5. I'm going to find the slope on the interval from 5 to 6, and that could estimate what happens at 5. And I'm also going to find the slope between 4 and 6, the slope on the interval from 4 to 6. And that has 5 in the middle of it. So if you want a little visual for it, and this is not the same function, not even pointing at the number 5 here, but if I wanted to estimate, for example, the slope at this point, then maybe I could estimate the slope between these two, or maybe the slope between these two, or maybe the slope between these two. And either way, I'm going to have some sort of slope that is, let me grab a pencil here. I could have a slope that does like this, or like this, or like this. But either way, it's kind of estimating what's happening here. Notice that the function is decreasing at 0, right? decreasing, decreasing, decreasing. We've got at least some level of decrease going on within this context anyway. So finding and estimating the slope at a point is really going to be best done by using points around it. On the left of it, on the right of it, on either side of it, however you want to do it. So we're going to do 3 different possible answers for this one. You don't always have to do all 3. Any of them could be taken in this context. So the slope on the interval from 4 to 5, well, that would be h of 5 minus h of 4 over 5 minus 4. And h of 5, let me slide this so you can see it. We're going to have 6 minus 0, so 6 minus 0 over 1, so 6. The slope at 5 is 6, maybe, or that's an approximation for it. Now, this is the value of the function. This is the approximation of the slope, okay? Complete coincidence, all right? Don't get your hopes up that always happens. The slope on the interval from 5 to 6. H of 6 minus h of 5. Well, that'd be 6 minus 5 in the denominator, so 1 down there. And we're going to have 14 minus 6. And that is going to give me 8. So maybe the slope at 5 is 8. Okay, well, let's try it again. H of 6 minus h of 4, or 6 minus 4, is going to give me 14 minus 0 over 2, and that's going to give me 7. So we have 3 potential slopes at 5, and well, an infinite number of potential slopes at 5 because it's an approximation, but our 3 approximations are 6, 7, and 8.